Hi everyone, and welcome back to Basic Math for Economics. In this video, we're going to use a matrix to actually solve a system of equations. So in fact, let's just jump in, and we call this reduced row echelon form, which is how we're going to manipulate a matrix in order to get a solution to a system of equations. So anyways, yeah, I want to use our matrix techniques to solve a system of 3 equations and 3 unknowns in this video. So this might seem a bit tedious. Some of you may prefer to use substitution for this technique, but this is a really powerful tool, especially once we move beyond 3 equations and 3 unknowns. It lets us organize many different equations, keep track of them, and manipulate them in a way that makes sense. So we're going to find that as our numbers of equations and knowns increases beyond 3, the ease of a matrix relative to traditional algebra is going to be increased dramatically. And again, I keep coming back to this, but this is really important when dealing with econometric equations. We use matrices the most when we're dealing with econometrics. So let's set up. Suppose we're in a situation where 3 firms are competing in quantities in a Cournot setting. You've calculated the first order conditions for each firm as follows. I've got 90 minus 2q1 minus q2 minus q3 equals 0, 90 minus q1 minus 2q2 minus q3 equals 0, and 90 minus q1 minus q2 minus 2q3 is equal to 0. Now these are actual first order conditions that you could get for a Cournot problem. And again, q1, q2, and q3 represent the quantities produced by firms 1, 2, and 3 respectively. So basically what we have right here is a system of 3 equations and 3 unknowns. We want to solve for q1, q2, and q3. So yeah, I could solve this using substitution, but it'd be cumbersome. So I want to use a matrix to solve for this. So let's set it up. The first thing we need to do is get this into a form that works for a matrix. So I need to clean this up a little bit. So the first thing I'm going to do is rearrange the equations such that anything that is attached to one of my variables, or q1, q2, and q3 in this case, is moved to the left-hand side of the equation, and everything else that's not attached to one of the variables is moved to the right-hand side. So now on the left-hand side, I have everything regarding q1, q2, and q3, and on the right-hand side, I just have 90, because it doesn't have any of the 3 variables there. Notice also that I've lined them up. I always have q1 coming first, then q2, and then q3. That's important as well. So from there, I can form a matrix, and the matrix is just going to be the coefficient of each variable as an element in the matrix. So basically, my first row in my matrix right here. So the coefficient of q1 is 2, the coefficient of q2 is 1, the coefficient of q3 is 1, because they don't have any number in front of them, and then that equals 90. So I get my first row right there, 2, 1, 1, 90. Second equation, second row, 1 for q1, 2 for q2, 1 for q3, and then 90. Third row, 1 for q1, 1 for q2, 2 for q3, and then again 90. And that lets me build my matrix. So being able to convert from a system of equations into a matrix is also a very important tool and a good thing to practice. But anyways, now that we have this in matrix form, we're ready to convert this in what we call reduced row echelon form, or just, it's a fancy way of saying just to solve it. So in order to do that, we have to manipulate the matrix until all of our diagonal elements, and the diagonal of the matrix is just when it's the same row and same column. So if you notice, I have 2's all along my diagonal right now, but they all need to be equal to 1. And then everything else that's not on the diagonal or in that final column where I have all my 90's has to be equal to 0. So you might be wondering yourself, how do we manipulate a matrix? Well, it's actually pretty straightforward. So basically, we can do almost any operation on any row of the matrix as long as we do it to each element in that row. And I can even take rows and add and subtract them together. So this is really similar to the video I produced on the elimination method for using algebra. In fact, it's directly inspired by reduced row echelon form. We're going to be doing the same thing but using matrices to do it. So anyways, let's actually jump right in. So if I look at the 2 in the first row and the first column, I need that 2 to become a 1 in order to achieve my reduced row echelon form. And I can do that by just dividing it by 2. So the important thing is, if I want to divide that 2 to make it a 1, I need to do that same operation to every other element in that row. So let's do that. Let's divide the first row by 2. So I do that, I get 1, 0.5, 0.5, and 45 now in my first row. But notice I haven't done anything to rows 2 or 3. I just did this to row 1. But I get that first value that I need. I have that 1 along the diagonal. Before I go and get the other diagonals, I'm actually going to get the rest of this column done first. That's usually a good rule of thumb. Start with a diagonal and then get the rest of the column complete. And I'll explain why in a minute. So in order to finish this column, I need the number in the second row in the first column to equal 0, and same with the third row in the first column. So in order to do that, I can use that 1 I just got in my first row. Basically, I can take my second row and subtract my first row from my second row, and that will give me a 0 for my second row. And that's really useful because it's going to allow me to get the values I need. Because, the only way I could use just a multiplication with that row by itself is by multiplying it by 0. And we all know that's bad algebra, and it really would make the whole thing break down. So anyways, what I'm going to do is I'm going to take row 2 and I'm going to subtract row 1 from it. So that's going to give me a new row 2. So the first element, 1 minus 1, 0. 2 minus 0.5, so row 2 minus row 1. 2 minus 0.5, 1.5. 1 minus 0.5, 0.5. And then 90 minus 45 and 45. But that gets me the desired result. The value in column 1 of row 2 is equal to 0 now, and that's what I need for reduced row echelon form. Let's do the same thing for row 3. I'm going to take row 3 and I'm going to subtract row 1 from it. And again, I get similar results. I get 1 minus 1 of 0, 1 minus 0.5 of 0.5, 2 minus 0.5 of 1.5, and then 90 minus 45, or 45. And that's it right there. My first column of this matrix is done. And it's really neat to do it this way because it gives us a really unique situation. So now, if I'm doing operations to get desired results in any other column, because there's a 0 in row 2 and row 3, I can now manipulate row 1 based upon rows 2 and 3, and that 1 that I have on my diagonal will never change because all of the other elements of that column are a 0. So I could take row 1 minus row 2, and it won't affect that 1 that I have in row 1. So that's going to be very useful going forward. I'm not going to mess up the work I've already done, which is why once we figure out a diagonal, it's useful to go back and finish the column, because then it makes it so that all the work you've done previously is not going to get, unraveled. So let's move on to row 2, or column 2 in this case, actually. So what we need to do first is we need to get the element on the diagonal equal to 1. It's currently 1.5, so I need to divide row 2 by 1.5. Okay, let's do that. Row 2 divided by 1.5 gives me 0, 1, 0.33, and 30. Well, alright, that's straightforward. We can usually get that diagonal result just by dividing. And again, I only affected row 2 right here. Well, from there, I need to get all the other elements in column 2 equal to 0. And again, I can do that by adding and subtracting, or subtracting basically row 1 and row 3 by row 2. But I can't just do a straight subtraction, because I can't do row 1 minus row 2, because that won't give me a 0. I need to do row 1 minus half of row 2, because that value in the second column for row 1 is half of the value of row 2. So I need to make sure I'm multiplying row 2 by a scalar before I subtract it from row 1. So it's going to be a combination of multiplication and addition in this case. So let's walk through this. I'm going to take row 1 and I'm going to subtract half of row 2. So that's going to give me 1, 0, 0.33, and 30, because, well, 1 minus half of 0 is 0. 0.5 minus half of 1 is 0. 0.5 minus half of 0.33 is 0.33. And 45 minus half of 30 is 30. And that solves that row for me. So again, I have that 0 where I want it to be. And I can do the same thing for row 3. So I get 0 minus half of 0 is 0, which is great. Again, that doesn't change. I get 0.5 minus half of 1 is 0. 1.5 minus half of 0.33 is 1.33, and then 45 minus half of 30 is 30. But look now, that second column is exactly where I need it to be for reduced row echelon form. And again, now I can do any kind of manipulations on that second column, and it won't change the value of the zeros or the ones that I've already put in there. They are set, they're good to go, and I don't need to worry about them anymore. All that's left to do now is our third column, and we just do the same thing as before. So I need the element on the diagonal to be equal to 1, which requires me to divide the third row by 1.33. So now I get 0, 0, 1, 22.5 on row 3. And that's it right there. All I need to do now is subtract a multiplied row 3 from rows 1 and 2. And again, it won't be a straight subtraction. I need to scale it. In fact, I'm going to need to scale row 3 by 1/3 in order to get the zeros I need in the rest of column 3. So first we'll do column 1, or row 1 in this case. I'm going to take row 1, I'm going to subtract 1/3 of row 3 from it. And that gives me 1, 0, 0, 22.5 in row 1. Because 1 minus a third of 0 is 0, 0 minus a third of 0 is 0, and 0.33 minus a third of 1 is 0. And lastly, 30 minus a third of 22.5 is 22.5. Do the same thing for row 2 and I get the same results. I get 0, 1, 0, and 22.5. And right there, that's actually it. The matrix is now in reduced row echelon form. All of the elements along the diagonal are equal to 1. Everything else except in the final column is equal to 0. And we are done. That's it. I mean, the steps are very straightforward, but we worked through them when we got all of our values. But more importantly, we've actually solved for our 3 equations with 3 unknowns. You may not have even noticed it, but it is done. Because remember when I told you that you needed to line up all the variables together, where the first column was x1, the second column was, or not x1, but q1, the second column was q2, and the third column was q3? Well, that's actually all 3 of the variables right there. So what is it saying to us right now? The first row of this matrix is telling us that q1 equals 22.5, or q1 star equals 22.5 in this case. The second row is telling you that q2 equals 22.5, and the third row is telling you that q3 is equal to 22.5. So if we, instead of having 3 equations with 3 unknowns, had 8 or 9 or 10 equations and 10 unknowns, this technique could save us a lot of time and organization in making this all work, and we would be able to solve it out, and that's what's important right here. So anyways, that's it for reduced row echelon form. That's all you need to know how to make it work. We can use it to solve large amounts of unknowns and equations together. So anyways, thanks for watching.